try to get a minimum sum of product solution for this thing. So let's implement it. So we've got that f is true if a is a 0, b is a 0, c is a 0, d is a 0. Is that all right there? So that term there puts a 1 there in our math. Okay, the next one is a is a 0, b is a 0, c is a 1, and d is a 0. So we get that one. Next one is a is a 1, b is a 0. A is a 1, b is a 0 is this row here. C is a 1, d is a 0. So that puts us over there. Next one is a is a 0, b is a 1 here. C is and d are 1s, so we get a 1 there. Then we have if a and b and d are all 1s, so a and b are 1s, d is a 1. So d is a 1 in these two cells. We don't care what, do that right, yeah, the other way around, here. That lights these guys up. We don't care what c is doing. Then we have b, c bar, e. So we don't care what a is doing. B is a 1. So B is a 1 here, don't care what A is doing, and then C is a 0, B is a, C is a 0, D is a 1. So that gives us that. Is that all right with everyone? Like the map? Okay, so every other possible combination of 0s and 1s gives us a 0. We don't have any don't care states that we could use to possibly simplify the math. So we'll go ahead and do a minimum sum of products solution for this. Any groups of 16 ones, 8 ones, 4 ones? Yeah. Okay, so we got a group of 4 ones here. So we're going to have B and D. Don't care what the variables A and C are doing, they can be either 1 or 0. So we got 3 more ones to cover. Can we put those into a larger group? 2. Okay, we can do groups of 2, right? So we can cover this one by putting it into a group of 2 here. No, can't do that. But we can go with a group of, that's right. There we go. Much better, yeah. Okay, so we can get a group of 2 there. So this is going to be A bar, B bar. And we don't care what C is doing, but we do care what D is doing. And so that's going to be D bar. Everyone okay? Got a lonely 1 there. Can we stick it into a larger group?
Yes.
And which is that?
The 2 corners.
These 2?
No.
Okay, this guy and this guy here. Okay, so that's going to be equal to, we don't care what A is doing, we do care what D is doing. It's a B bar. And then C, D bar. Is this a unique minimum sum of products? Are there other possible ones?
No.
All right, so we want to implement this thing, and I told you to use only 4 input ANDs, as many of them as you want, but we can only use 4. So we're going to have our 4 inputs, A, B, C, and D. If we need the complement, we'll have to generate it. These are just our 4 inputs. So we're going to have to generate the complement for what? A, B, and D. So we'll generate the complement for A. So using a 4-input NAND gate, this is one particular option that we can do, is we can run those all into, we can run that A variable into the 4 inputs on that NAND gate. There are other possibilities. What would I want to, if I wanted to tie some of the inputs to either low or, well, I'll do that on the next one. So let's generate, we need B bar.
Dr. Brown,
Yeah.
what like clued us in that, like how do we know the difference between 4 input NAND gates and like 4 NAND gates with inputs?
Common sense.
Well, everyone put, or Taylor helped me. And we thought it was, we read it as 4, like, only can use
Well, now,
4.
did I not say any number?
Well, you didn't know.
No. Did I say that on the paper?
Yeah, I think I did the same thing they did.
It just says 4 input NAND gates.
Yeah.
Yeah.
Okay, so I should have had a hyphen in.
Yeah.
I thought he meant like 4 inputs.
Yeah, I could have read over that for a second.
Well, no, because he said 2 inputs when you did the one in class.
Yeah. I mean, I told you, that you could have as many inputs on these gates. You could have 2 input, 4 input, up to 8
Yeah,
inputs.
okay, I remember that, I wrote that down, you said okay, but just when you read it, it seems like you can only use 4 total.
It would, well, in this case, it would actually, except for the negation, you could get by with 4 Ds. But we need more because we got to do the negations. So after this, is there, if I told you that you're going to use 3 input OR gates, do you understand what I mean? There are OR gates that have 3 inputs.
So what is the difference then between a 2 input and a 4 input?
2 inputs.
So it's just like an arbitrary, then, well, I guess like looking at this one where you have 4 going into the NAND gate, why do we have 4 versus like the 2 then? Like what does that
Because
do?
you, as a designer, are going to determine what package you're going to use. So the thing we're going to talk about after we get done with this is start talking about the physical attributes of gates. And so you, as a designer, could go out and you could buy 2 input gates, you could buy 3 input gates, you could buy 4 input gates. So, all right, so I've got another NAND gate here, and I'm going to tie 3 of these guys either to a high or to a low. Which one do I want to do?
Wait, because we'll take the lows and make it a high.
Okay, you got a 50-50 shot at this. How many highs?
1.
One high, that's appropriate. How many lows? This is a binary decision. You have to make up your mind. There's a bunch of don't cares out there. What did I tell you about a NAND gate? Any input, what? The output is what? Any input low, the output is forced high. Well, what happens if you tie 3 of them to low? The output. The output is what? Does it matter what A's doing? No. You see? So what do I want to tie it to? So if I want, I can tie that to a logic level high, and now that gate will function as an invert. If A is a 0, a 1 comes out. If A is a 1, a 0 comes out.
So you have the B directly connected to the NAND gate, and then 3 of them like kind of grounded to 1. Is that what that is? Not grounded, but like connected. Connected. Jesus.
Yes. Yes.
Can we explain one more time why you chose the high instead of low?
Any input low, the output goes high. Well, if I tie 3 of them low, the output is guaranteed to always be a 1. Doesn't matter what the
But
other
didn't
input
we
is
just
doing.
tie them all to high?
Does that make sense? Yes, sort of.
And why wouldn't we do that with A also? Or is that
A
this?
is a variable.
But we're doing this for B, I thought.
I mean, B is a variable. B's are variable. Sorry. So if B is a 0, a 1 comes out.
Okay.
B is a 1, 0 comes out.
Oh, because you have zeros and ones with
Okay.
You're just doing it 2 different ways. You're negating the
I'm
variable in
yes,
2
I'm
different
doing
ways.
it. I'm showing you a couple of different ways to do this. Now, some of the physical attributes of gates are the fan out. You can only take an output from a gate and tie it, our rule of thumb is to 10 other gates. So if I was taking this B, or this A here, and tying it to these inputs, well, it's separate gates, I don't think that bad, but you sometimes have to be careful of how many gates that you actually tie this thing on. Tying it to these 4 wouldn't matter one way. So, a couple of ways that we could do that. All right, we're not done yet. What do we gotta do? We gotta get a D bar. Okay, so we're gonna take D bar, and just for something different, I'll tie D to 2 of the inputs, and I'll take the other 2 inputs, and what should I do with them?
Make them low. Make them high.
Make the 2 high.
Make them both hot. Yes. Doing all right. Okay, so now, I told you that the AND is a universal gate, that we can make any function we want with it. Well, what we're trying to do is implement a product or sum of products solution. So a first set or column of NANDs followed by another NAND gives us the ANDing and ORing capability so we would get with AND gates and an OR gate. So now what I need to do is B and D. So here is B and D. But I'm going to tie those into an AND gate. So I'm going to take the B and I'll take it to 2 of the inputs, and I'll take the D to 2 of the inputs of the NAND gate. I could have other possibilities here. Then I need to generate this guy here, A bar, B bar, D bar. And I should have, well, I'll do it like this. So I need the A bar, I need the B bar, and I need the D bar. So I should have brought these guys over and then made a column of the negations. Yeah.
On the parts where you connected B and D with the NAND gate, when you have it like 2 split off and then 2 split off, if you don't like say that that's connected to 1, are we still assuming that that's just gonna be 0? Like, why did you branch them but not connect it to anything?
What do you mean not connected? You're talking here?
Yes.
What do you mean it's not connected to you?
Well, like, before we put it to a 1, when we branched both sides.
No, wait. how many input NAND gates are we using?
Oh, 4, sorry.
Let's count them.
Oh, okay.
1, 2, 3, 4. Yes. Are you okay with it?
Mhm.
Everybody all right?
Does it matter that you chose D to have 2 for the last part, opposed to A or B?
Completely random. Everybody get the sign-up sheet signed? We're supposed to keep roll for 3 weeks, so I will do that through Friday, and after that, you're still expected. Any other questions?
What exactly does the third NAND gate correlate to? Which term?
We're trying to generate this guy here. What we're generating, at this point here, this is B, D, that whole thing barred. This is A bar, B bar, D bar, barred.
So the bottom one should be offset from everything, like that's connecting the first 3 terms. Or the first 3 NAND gates.
Where?
So I was just saying, like, the position that it's in, it should actually be like off to the side because you're connecting the first 3 NAND gates to get that term at the bottom.
Yeah, it's just on the bottom of the board.
Okay.
Yeah.
I think I see some, all right. Okay, so let's do it again. So out here, I'm going to do, I want B and D. This guy has got to go over to B, this guy has got to come to. So this is A, B, that whole term, negate it. Everybody all right with that? B, D, B, D. B. Better? Okay. All right, so now we need to generate the next term, A bar, B bar, D bar. So A bar is going to be here. Something completely different. I'm going to connect that to the first of the second terminal of my 4 input NAND gate. And then we need B and D bar. Is that all right? I need one more term there. I need to generate the B bar. Need to generate C. C's coming all the way from over here. And I'll take C to 2 inputs. And then I need a D bar. Then what do I need to do after that? Put those into a NAND gate. Okay, I've got how many inputs on the NAND gate? 4, because I'm telling you that's all you can use. I got one more input here. What are my possibilities of doing something with it?
Put one of the others in twice.
Okay, one of these 3 in twice, or
Pull it down
tie
high.
it high. Okay, so let's, just for something different to do, let's try to tie that guy high. And so here is my function out. Ready? Okay. What do you suppose, what do you suppose I could implement in terms of a logic function with only NOR gates? You do a minimum product of sum. And again, sometimes one might be slightly more advantageous than the other, minimum product of sums or minimum sum of products. I'm only